When you look around, have you ever really thought about how all this stuff exists? From the salt in your shaker to the very air you're breathing? Well, the secret isn't some super complicated magic. It's actually all about the social lives of atoms. Today, we're going to dive into chemical bonding and see how these tiny little particles hook up, form relationships, and build, well, everything. All right, so here's the game plan. We're going to start with why atoms even bother teaming up in the first place. Then we'll get into the one simple rule that decides how they do it. After that, we'll look at the two main ways they bond, by taking or by sharing. And finally, we'll see how those two simple actions create, well, the entire universe. Let's get into it. Okay, section 1, the quest for stability. This is all about the why. Why can't most atoms just be loners? We're going to find out their core motivation for getting together. So that's the big question, right? Why are atoms almost never found just hanging out by themselves? Well, you can kind of think of them like people. They're always searching for a more stable, a more comfortable situation. And for an atom, that comfort and stability almost always comes from pairing up with other atoms. But what does stable even mean for an atom? It all comes down to their electrons, especially those electrons on the very outside edge, what we call the outer shell. The number one goal for pretty much every atom out there is to get that outer shell completely full. That's it. That's their version of complete happiness. And if you want a perfect example of this, just look at the noble gases. Elements like helium or neon. They're basically the cool kids of the periodic table. They're born with that perfect, full outer shell, so they're completely stable and content on their own. They don't need to combine with anybody. Every other atom is just trying to be like them. All right, so we know atoms want a full outer shell. The big question is, how do they get it? That's what this next part is all about, the deciding factor. It's pretty amazing, but it all comes down to one single rule. So here's the dilemma for an atom, right? To get that full shell, does it just snatch an electron from a neighbor, or does it try to find a partner and share? How does it make that call? Well, the answer is this one simple idea: electronegativity. That's a fancy word, but all it really means is an atom's pulling power. It's a measure of how badly it wants to grab onto electrons in a chemical bond. And this one little property is basically the entire rulebook for how atoms interact. And this simple rule creates two main paths. Think of it like a tug of war for electrons. On one side, if you have one atom that's way stronger, it has a much higher electronegativity, it's not really a fair fight. That stronger atom is just going to rip the electron away from the weaker one. Boom. That's an ionic bond. But what if the two atoms are pretty evenly matched in strength? Well, neither one can win, so they have to compromise. They agree to share the electrons, and that's what we call a covalent bond. Okay, so let's dig into that first path. Ionic bonds, the takers. This is what happens when that tug of war is completely one-sided. Now here's a really important thing to get. An ionic bond isn't like a physical rope tying two atoms together. It's an attraction, a really strong electrostatic force between two atoms that now have opposite charges. Seriously, just picture two magnets snapping together. That invisible force holding them tight, that's the bond. So the atom that loses the tug of war, the one that gives up its electron, that becomes what we call a cation. And since electrons are negative, losing one means the atom is now left with a positive charge. And hey, here's a little trick. The T in cation kind of looks like a plus sign, positive. And on the flip side, the big, strong atom that took the electron is now an anion. It gained a negative electron, so its overall charge becomes negative. So you see what we've got now? A positive cation and a negative anion, and opposites attract. So let's just run through that one more time. Step 1. The weaker atom loses an electron and becomes a positive cation. Step 2, the stronger atom grabs that electron and becomes a negative anion. And step 3, the new positive ion and the new negative ion are powerfully attracted to each other. That force, right there, that is the ionic bond. Simple as that. Okay, so that's what happens when one atom is a bully. But what about when they're evenly matched? That brings us to our next section. Covalent bonds, the sharers. This is all about cooperation. A covalent bond is a totally different ballgame. It's a real partnership. It's a chemical bond where two atoms actually share a pair of electrons. So instead of one taking and one losing, they both pitch in, and the electrons basically belong to both of them at the same time. And why do they do this? Well, the goal is exactly the same as before: stability. By sharing electrons, each atom gets to pretend that the shared electrons are in its own outer shell. This little trick lets both of them get that full, stable, noble gas setup they're looking for. It's a total win-win. Now, this whole sharing thing leads to some pretty specific characteristics. Stuff made with covalent bonds, we call them covalent compounds, usually has low melting and boiling points. I mean, think about it. Water, the oxygen you're breathing, those are covalent. They also don't conduct electricity very well, because unlike with ionic bonds, you don't have those charged particles floating around. All right, let's wrap this up. We've talked about taking, and we've talked about sharing. Just two basic types of bonds. But this is where it gets mind-blowing. This section is called Two Bonds, Endless Worlds, because it's incredible how these two simple rules are enough to build everything. So here it is, all laid out in one place. Ionic bonds, that's when there's a big difference in electronegativity, so electrons get straight up transferred. You end up with charged ions. Covalent bonds, that's when the electronegativity is similar, so they have to share electrons. It really all comes down to that one thing. A huge difference in strength leads to taking, and a small difference leads to sharing. That's the whole story. And that just leaves us with this one last thought. It's kind of amazing, isn't it? The simple act of taking versus sharing an electron, that's it. From those two basic interactions, you get literally everything. The salt, the water, the air, us. An entire universe of incredible complexity, all built on a couple of really, really simple rules. Makes you wonder, what else works that way?